Well, hello everyone. For those of you that don't know me, my name is Mark Hanchett, and I am the CEO of Atlis Motor Vehicles. And I am coming to you from my house, which actually used to be the former headquarters of Atlis Motor Vehicles when we got started. We've now moved into a facility up in Northern Mesa. And today we wanted to talk to everyone about battery technology, what we're doing at Atlis Motor Vehicles, why it is super important, and sort of what the roadmap looks like for us over the next 9 to 12 months. And we're going to dive a little bit deep into some of the details, and I've written some stuff on the board here that we're going to dive into. We're going to show you a couple of pictures and things like that. To start off with, we should probably get to, what is Atlis Motor Vehicles? What are we about? What are we doing? Now, most of you know us as an electric vehicle startup that is focused on building electric pickup trucks, very specifically trucks that are dedicated to doing work. Our focus is on trucks that can do real work. We're not really focused on doing commuter trucks, although that is super important to us, and that's a very important market segment for us, but we're really trying to build vehicles and technology that can support this idea of doing the things that you do today with your gas or diesel vehicles. We don't want to necessarily take a step back, we want to take a step forward. And our team is built of individuals that fit this sort of genre, that fit within this ecosystem. We are all a bunch of people that use trucks for work, we use trucks for play, we dedicate our sort of our transportation lives to that very specific vehicle segment. It's the one that is most interesting to us. And the reason why we're doing this is, more importantly, we see the movement towards electrification. That's super important. But if we're not making that leap forward, if it feels like a step back, if range suffers when you're towing to a point where it makes it impractical, if you can't do the things you do today, that doesn't make sense to us. We feel like if we're going to change the world, everything simply has to be better. And that's what's important to us, is making that leap. It's not simply building something that's compliant, not simply building something that sort of does the job, but something that makes that massive leap forward. And that's what we're trying to bring to the market. Now, our focus today is on trucks. That's the most important thing that we see right now. But of course, all of this technology that we're building has applications in various different spaces. And Atlis is not just an electric vehicle company focused on building trucks. We picture ourselves or view ourselves as an electric vehicle technology company that is building different components of technology that will be applicable to various different verticals within the market space. Really dedicated to work, though. We're not going after consumer vehicles. We're not necessarily going after the shared vehicle market, where we're talking about things like Uber and Lyft. We're really focused on the work segment and everything that has to do with that particular market. Now, a couple of weeks ago, almost a month ago, we did a sort of impromptu battery day, as well as the ribbon cutting ceremony as we moved into our new facility. And as part of that, we presented a small mock-up of a battery pack that charged in about 22 minutes. That, in this particular industry, is really difficult to do. Now, we say charged in 22 minutes. What we mean by that is not 5 to 80%. What we mean is the customer will experience a 0 to 100% fill up of their vehicle. In that particular case, 22 minutes. And we got to, introduce the team and everyone to some of our investors, some of our followers, some of the people that are very interested in what we're doing. We got to meet some of them and get some of their feedback. It was really a fantastic event. But since then, although we've always pitched 15 minutes, since then we've gone from 22 minutes all the way down to 9 minutes, 36 seconds, then 9 minutes, 26 seconds. And that is unprecedented in the industry. That is something that no one else is doing today. There are a lot of claims around miles per hour and things like that, but no one today is really, truly doing that. Now, why that actually matters is super important, because when we look at work in general, as we start talking about some of these different use cases and opportunities within the work truck segment, the first thing we always try to focus on is time in your day. That's the one most important thing that you can never, ever get back. It's the one most valuable thing that every single one of us has. And when we look at electric vehicles and trucks and what others are developing, or what's sort of coming into the market in the current technology, the one thing that really bothers us is how much time you actually have to sit down and charge that vehicle. There are different solutions to this being proposed. We went down the route of trying to solve the battery problem. But what's most important to us is, after you've spent your whole day at work, at the end of the day, the one thing you don't want to do, the one thing that you really don't want to focus on, is going somewhere, having to plug in, wait for an hour for that vehicle to charge. Now, there is the caveat that you could charge at home, but for, say, utility customers that use a company vehicle and then they go home afterwards, for them to charge at home, that starts building this logistics problem, this accounting problem, where they have to negotiate, well, who pays for that power? Because that's coming out of your personal electric bill. And if the company pays for that, how do they properly account for that? How do they properly bill for that? That creates additional problems in that workflow that we simply don't want to introduce in the system. It's not something you have to solve today. Why would we build something and make you solve that tomorrow? So one of the most important things is, of course, throughout the day, if you have to charge by the end of the day, the one thing you want to do, again, is go home. So with Atlis and the technology that we're proposing, or that we're actually developing here, is a solution that allows you to spend no more than you would normally spend at a gas station filling up a diesel or gas truck today. Whereas the competition today, if you were to do that, you're looking at potentially an extra hour, maybe 30 minutes for 80% of that capacity at the least. But typically about an extra hour of your day. That's an hour you can't get back. Yeah, you could watch Netflix or you could watch YouTube while you're doing that, but if you got a family like me, it's picking my kids up from school, it's going home, it's spending time with them, it's getting home in time for dinner, and that's a super important thing, and we want to make sure that we continue to facilitate that. The next aspect of it, and the reason why we're doing this, is because we're talking about vehicles that can tow and haul. And that is one of the most important aspects for pickup trucks. If you have a truck, it's this concept and idea that you can do something with it, whether you're going off-road with it, or whether you're towing a fifth wheel with it, a camper, maybe it's a horse trailer, whether you're towing a trailer out to the job site, whatever it happens to be. Maybe you're hauling stuff across country. That's what my father did for several years. The amount of time that you actually spend down is time lost, right? That's money lost, that's time in your day lost, that's throughput that you can't actually achieve. These things are super important. And when you're towing something heavy, just like in your gas and diesel truck today, your mileage drops, right? So your range starts to drop. And when we start talking about hauling long distances, maybe it's just a few hundred miles, maybe it's a few thousand miles cross country. When you start looking at the fact that, okay, well, if I can only drive, say, 150 miles at a completely full load, that's maybe 2 hours, 2.5 hours of driving. In a typical scenario, you're looking at 3+ hours of time, because it's 2 to 2.5 hours of drive time and then an extra hour of charge time. And that's completely out of the norm for today. I don't know about some of you, but for me, when I'm traveling with my family, when we're doing road trips, it's super important that we simply don't spend a lot of time just sitting still. Sometimes we want to get somewhere and we want to do something. That's why Atlis, we're focused on reducing that time that you spend charging. That's super important, because when you're towing and hauling and you go from, say, 500 miles of base range, and you drop that down to 150 miles, it's completely unacceptable to have to spend another hour sitting still. You want to spend 15 minutes, use the restroom, grab a bite to eat, right? Get back on the road and keep going. And that's why we're doing this. That's part of the reason why we're placing such a large emphasis in this. The second piece of it, of course, is how can we reduce the infrastructure cost that's associated with all of this stuff. As we sort of look to that and we look to what's happening in the future, we're trying to find a way to reduce the amount of infrastructure that we have to deploy. Let's turn a potentially $1 trillion problem into a $500 billion problem. Let's cut that in half, or perhaps even do better than that. Let's develop something that doesn't require us to potentially spend a tremendous amount of money to start to roll something out fast. Let's reduce that cost. Let's push that out faster. Let's get more throughput going, 4 times the throughput that you can get with a charging station today. That then allows us to facilitate rapid adoption of electric vehicles. And that for us is super important. Now, as we sort of look to where we would develop and sort of deploy those charging stations, one of the most important things, of course, is focusing on highway corridors, whether that's in cities or in between cities. That is one of the most important things that we find valuable. But by reducing our charge time, by allowing us to get more throughput per stations, that's less stations we have to deploy in little bitty areas. And it's more stations, or stations more frequently along those highway corridors. Let's try to reduce some of that range anxiety. Some of you probably own a Tesla today. You drive that thing in between cities. You've driven that to maybe some more remote areas. I know this past weekend, we had an incident on one of the highways here where a truck overturned. We had to backtrack. Having that inability to maybe stop somewhere along the way or deploy more charging stations, as we all know, that's a hiccup for us. But it's expensive to do that. And if we can reduce that cost, if we can drive that cost down and deploy more of them, maybe less at each location, but more of them, or more charging stations more frequently, then we can eliminate some of that range anxiety. And if you're only spending 15 minutes there, if there's 2 of you, there's one in line 15 minutes and then another 15 minutes, that's not a long time to wait. Now, how does this all sort of translate to the end customer? What does this mean when we start talking about 15-minute charge times? If we're using the Tesla metrics, we look at this chart where we see the charge speed go up to about what they claim is 1,000 miles per hour for a very short window. That's ultra fast. Everyone gets excited, right? Because in 5 minutes, you can add maybe between 50 and 100 miles, right? And then it sort of tapers down from there. So if we're using that metric and what that translates into from an Atlis perspective, at our peak charge rate, we're looking at about 3,000 miles per hour. It's about 3 times what Tesla is doing at the fastest rate they are today. In our particular case, it's 6 times the capacity of that cell or that actual battery pack that's inside there. So if it's a 500-mile range pack, we're charging at 3,000 miles per hour. If it's a 300-mile range pack, right, we're charging at 1,800 miles per hour, just simply because you can't necessarily put more energy in because the pack is smaller. It's really dependent on how much you can actually pump into that cell at any given time. Now, when you look at a comparison between, say, us and some of the other companies that are in the industry, we don't advertise, or we're not aiming for a 5 or 10 to 80%. That's not really practical in our particular use case. We're really trying to focus on whether or not we can actually push vehicles out there and pitch this idea that's very similar to what you have today in your gas or diesel vehicle. If it's empty, it's empty. If it's full, it's full. And if I fill it up, how long is it going to take me to get that full capability out of that vehicle? Not 80% of that capability, but the full thing. And that we find super important, especially when you start talking about towing again. We start talking about going down to, say, 300 miles, 250 miles, maybe all the way down to 150 miles. 80% of that is no longer enough. You really need to push that as far as you can to get every last little bit out of that as you possibly can. Now, as we sort of look to solving this problem and we're trying to push advancements in battery technology, some of the more critical issues that come up is always safety. It's always, well, how are you solving these different problems that are associated with charging a battery very quickly? There's dendrite growth, right? These little spiny things that start to grow on the anode and it crosses over to the cathode. And when that happens, right, you get a short across that. And when that happens, you get a lot of energy being dumped through there. You get a hot spot that grows. Eventually you get a, right? You get a Samsung phone incident where this thing heats up and it starts to burn and it starts to pop. Well, that's a very dangerous thing. It's something that we take into account in everything that we do today, and it's super important for us. The other side of it is the one that a lot of people don't actually focus on is on the mechanical aspects of it. So as you're pumping a lot of energy into that cell or pulling energy out, as those temperatures change within that cell, you get these different sort of characteristics that occur inside there where the anode and cathode, the electrodes inside there, they start to pull apart from each other. They start to separate as things start to expand and as they start to contract. Well, when that happens, you get this incident where you get these little wavy systems here where maybe the distance between the 2 points here are a little bit smaller, it's a little bit further here, and when you're transferring energy across from that, you actually have a concentration of energy that's flowing in that tiny little section. There's a concentration of ions that's flowing there. It's not necessarily even, although these are very, very small spaces. What we see when we start tearing these cells apart, and there's been studies done independently on this, is that you start to see failure points at these little wavy lines here, or at these points where things start to separate. And that's super important in terms of dealing with the thermal issues related to ultra-fast charging. Those are some of the things that Atlis is trying to solve here. That's one of the things we had to solve to be able to accomplish this. Now, part of that is picking the right construction. Now, cylindrical cells are rolled. A lot of pouch cells are typically rolled, and a lot of prismatic cells are rolled. The other design is typically a Z-fold design. This is actually a much more robust design outside of a cylindrical cell. With cylindrical cells, yes, they're rolled, but as you look towards the center of that and you look at that construction, as it expands and contracts, you still get this issue. You can also get that issue with a Z-fold, but what we're actually doing from a mechanical aspect is we're making changes to how that cell is actually put together to ensure that we minimize the risk of something like this occurring. I'll talk about dendrites here in a little bit and what we're doing there, but we're actually using a Z-fold design, and we're developing a very proprietary sort of anode and cathode electrode layout and construction that allows us to minimize those thermal expansion problems that occur in there. All of this is kind of leading not just to fast charging, but also this ultimate goal of achieving longer ranges or greater usability for that vehicle. In particular with trucks, it's super important that we do something where it doesn't just last 500 of these cycles. It really has to last 2,000 of them. We have to hit this point where this vehicle will last the expected life, which is 10 years of that vehicle. And to get there, the line that we've kind of drawn in the sand here is about 2,000 cycles. from our perspective, if we can get around 2,000 cycles, we should be able to hit that 1,000,000 mile mark. And today, with the data that we're collecting doing these fast charge cycles, what we're seeing is that in cells where they typically perform with 2,000 cycles or above from a standard operating spec, we are seeing a trend in the life of that cell that would suggest that we are going to either meet or exceed that requirement. Currently today, we don't see any data that suggests that we're degrading the life of the cell, and that's super important. That's one of those key aspects of, if we charge this fast, how long is it going to last? And from our standpoint, it is incredibly important that we do that. This is trucks, right? This is expected to go a long ways. It's expected to go 500 miles. We want to hit 1,000,000 miles for these because that sort of fits within our business model. That fits in the use case. That fits within what our customers are asking us to be able to do. And that is incredibly important as we try to actually do that. Now, how are we sort of doing some of this stuff? It's super important that we look at the, what Atlis is doing, but we also want to look at what everybody else is doing in the market too. The first thing is there's different types of cells out there. If you're looking at solid state cells, most of them today actually come in a pouch form. There are other ways to develop that, but in the end, from a form factor perspective, you pick it up and it's a pouch. I know inside it's a little bit different. And the technology that we're developing actually allows us to kind of solve some of the problems that you're seeing in solid state cells when they're trying to get those fast charge times, high energy density for those long cycles that you're looking at here. But today, typically in most EVs, you'll see a pouch cell design in things like the Chevy Volt and the Bolt. You'll see that, I believe, in the Audi electric vehicle and a couple of other ones that are on the market. And they come in two different forms. This one that I sort of drew up on the board here is typically a very long cell. It has tabs on the end. They're typically big tabs. They're power tabs. The other configuration there is simply a big pouch with two little tabs on top. In terms of pouch cells and why, although we've done development with those because they're very cheap and easy to build from a prototype perspective, the reason we're not using those from a long-term perspective and using something that's more closely tied to, say, a prismatic cell is because pouch cells are very sensitive mechanically to handling. They're very sensitive to pressure buildup. They're very sensitive to temperature. They're very sensitive to a number of different things. They're not super robust and they're difficult to handle. So we've actually walked away from some of the pouch cell technology. I know it's cheap to build, but if you do some other things with kind of the prismatic approach, we can actually drive some of that cost down and it becomes comparable to this. Now, the prismatic cells, I'll touch on this in a minute, but the prismatic cells, those are used by some electric vehicle makers, particularly in Europe. There's a couple here in the US that are doing that too. And typically they come in these big bricks, anywhere from 40 amp hours, maybe 20 amp hours, all the way up to, I've seen 220 amp hour cells. These big, huge bricks of cells. Sometimes they follow a Z-fold design, but typically they're actually built with a rolled design. And when that happens, or when they build it like that, it's stuffed into a container. And when they do that, there's these huge gaps here. They're actually somewhat inefficient from a design standpoint. And those gaps, when we start talking about the thermal expansion and contraction of that material, when we start talking about mechanical vibration and various other things, remember I talked about how some of the anode and cathode layers start to separate from each other to start to do different things. Well, that actually occurs up here and it occurs here because there's room for that to expand. Now, there is a way to solve that. You simply just build a container that could eventually hold that. But then as you start looking towards the center here, where you get those real tight squeezes, those real tight loops, you actually start to see failures there. Not simply because of any charging or discharging behavior, but because mechanically you've bent that in such a tight corner that you will actually start to see failures within that active layer, whether it's on the anode or the cathode that's there. But prismatic cells they're widely used overseas. They're widely used around the world. They are typically a very robust design. Sometimes even prismatic cells are simply a mechanical container that contains a bunch of pouch cells inside there. We've definitely looked at that technology, but when we're looking at this and the prismatic cell designs and even cylindrical cells, when it comes to thermal management, they're all bad. They all have very, very poor designs. They're not very good at pulling heat out of the cells. They're not very good at necessarily pushing heat back into the cells. From a mechanical construction standpoint, with relation to the thermodynamic principles, or these three designs are actually super poor. Now, the final one here is the cylindrical cell that's used by a large number of auto manufacturers that are out there today. We're actually doing some testing with those, but there's a number of studies out there that talk about those. We've seen it ourselves in some of the studies that we do. The problem with cylindrical cells is if you're cooling it with a cold plate on the bottom, or you're cooling it with a channel on the side, you're not getting even cooling characteristics throughout the entirety of that cell. And in particular, from the top to the bottom, you might see a difference of maybe 2 to 3 degrees C. From here to here, you might see a little bit of a difference there as well from the outside of the cell. The problem is actually really, it's dead nuts in the center there. It's right in the center of that cell. And that same problem occurs here with pouch cells and very much so with these very large prismatic cells. And one of the sort of key things to fast charging a cell is being able to properly manage the thermal characteristics of those cells. Chemistry does play a role in it, but there are some things you can do from a thermodynamic perspective to offset some of the challenges that we're facing on the chemistry side. And unfortunately, these three particular designs are not very well suited to properly thermally managing the characteristics of those cells. Cold plates are particularly bad because they only start from one side and you have to move up. Now, you could fill a bunch of these with epoxy and create a big brick, but you're still cooling from one side, right? So you're still trying to pull heat from the top down. And typically, if you have energy transfer going over the top, that's usually the way some of those designs are actually implemented. You do get a lot of heat up here, and you still have to cool that. If you're drawing a lot of current from these cells, those tiny little tabs that are in here, there's little tabs here, and of course the tab here, this is actually a hot spot right here where that's welded. When it comes to trying to cool those, if you're generating a lot of heat here and you're cooling from the bottom, or vice versa if it's flipped, but typically they're all set one way. If you're trying to do that, you're not very efficient up here. That's not super positive in terms of getting the most out of the vehicle that you possibly can. The same thing is true with prismatic cells because all of that energy is typically pulled out of the top. Yes, they do have a large number of conductors that are in here that are sometimes connected to those tabs on the top, but typically when you're cooling these, you cool from the side or you cool from the bottom, and right there in the center of that, you see a very, very big temperature difference. You could see anywhere between 5 degrees C all the way up to 10 degrees C or more. And when you're pumping a lot of energy into that cell or pulling a lot of energy out of that cell, that temperature differential can mean a great number of things. That can be a massive problem in terms of efficiency, but in terms of life, if you're looking at an electrode that's inside there, if at the very center, let's say that's on this end and this is wound up inside there, yes, over here you might not see a lot of failure, but over here on the inside where it gets super, super hot, that's where you start to see some of those active layers start to separate, they start to fail. That's where we start to see problems in some of those cells. So one of the things that we have placed a tremendous amount of focus on is actually trying to solve some of that. And that's one of the key things that Atlis has been tremendously focused on, is solving that problem of thermodynamics. Because if we're going to pump a lot of energy into the cell, we have to be able to pull energy out. There's always resistance or impedance in there, whether it's through the chemistry or through the mechanical construction. There's always an inefficiency there. And when we're trying to pump in as much as 6C or 6 times the capacity of that cell in at any given time, it's super important that we manage the temperature at the very center of that. Now, I talked about cooling plates on one side of it. Another way is to cool on the side of a pouch cell, but when you're doing that and you're trying to transfer energy across from those electrodes, maybe you have an anode, you have a separator and a cathode there, that separator is actually it's a mechanical insulator as well as an electrical insulator. It's very difficult to transfer heat through all of those different layers in parallel like that. There are some studies out there that you can pull heat from the pouch cells, from the ends and from the tabs, and yes, that works, but typically pouch cells are designed in very, very long lengths. You could try to pull it from the side and everywhere else, but you don't have a direct connection out there. Now, Atlis's kind of proprietary cell technology and what we're developing is in building a type of prismatic design that takes concepts of the pouch design, uses some things from a chemistry perspective, takes a Z-fold construction from the inside, and what we actually do is we pull energy out both the top and the bottom. And we do that through a number of different things from a mechanical perspective that not just allows us to pull heat out, but allows us to pump heat in. And by doing that, and by very precisely controlling the thermodynamic characteristics of the cell, we're actually able to control it to the point where we might be seeing maybe a 1 degree C difference between the center of that cell and the edge of that cell. And that is incredibly important. If you're trying to charge something fast, yes, you're going to face some chemistry barriers in doing that, but there are a number of different things you can do to overcome that. And part of that is what we do from a thermodynamic perspective. Now, I'm not going to talk about what we're doing inside that cell to be able to accomplish that. That's kind of some of the proprietary stuff that we're doing today. But in line with that, that's one of the reasons why we are actually able to charge a cell very quickly. There's some public information out there about heating cells up and reducing dendrite growth. Remember, I said I would talk about this earlier today. This is super important. These other things relate to failure, but the one thing that everyone's trying to look for is dendrite growth. They're trying to avoid this concept of running into a point where you get a short inside the cell and you get a runaway condition, something that you can't actually overcome. It's something that's just simply, if it does occur, it's going to happen, and the only thing you can do from there is mitigate. Our approach is actually using, and there's some independent studies out there that have now confirmed this, but our approach is actually, we operate at a temperature during the charging process that is above the threshold, the point where dendrites grow. We actually raise the temperature of that cell up, and as we're pumping energy into it, it's super important that we keep, again, 1 degree C difference from the center to the outside edge of that, but raising that temperature up to a threshold above a point where dendrites typically grow. Now, will they grow? Yes. It's always going to occur over time. And there's some different things that we do throughout the life cycle of the vehicle to break those off, to heal those, to do various different things. We won't necessarily touch on those, but again, when we start talking about some of this stuff and where it goes, our test data so far today is suggesting that we're still good. Everything that we've done today suggests that we'll still meet our 2,000 mile vehicle or 2,000 cycle 1 million mile performance with very little to no risk of dendrite growth, and that is incredibly important. Part of it is operating at this threshold above where it typically grows today. And we'll post some links here on social media and stuff like that to some of the independent studies for that here in the next couple of days, but that's one of the sort of key secrets. The other side of it is what we're doing from a mechanical perspective. We're pulling heat out and pushing heat in and maintaining that 1 degree C difference that's out there. That's incredibly important when we're doing that. The other side of it is trying to bring that impedance down as low as we possibly can within each cell that's in there. One of the challenges is, especially in our particular pack design, where we actually operate at 1600 volts, 800, or 400 volts, and the pack is dynamically configurable that way. We've been working on that for a little over 2 years now, is that we have to make sure that we are balancing those cells appropriately. We also have to make sure that we're developing battery management systems that are independent from each other. So in each 400 volt, or it's actually a little bit less than 400 volt, but each section of that, we actually have an independent battery management system that's in operation. And what that's doing is it's very rapidly ensuring that each cell within that parallel or series configuration is balanced. And we do that at a very rapid pace. Typical BMS systems today, they balance in the milliamp current rating. So if you're transferring either energy through a power resistor and dumping it, which is horrible, or you're doing active balancing between two cells where you're moving energy from one cell to another one, they typically do that in the milliamp range. But when we're talking about pumping a lot of energy into that cell, we can't operate a balancing curve or a balancing characteristic in milliamps, because we have to account for the fact that there will be variations in impedance of those cells. But through chemistry selection, and right now it is an NCM-based chemistry that we're actually using today, with a couple of different additives to start us off and do some things like high cycle counts. There's also some active layer things that we're doing there as well. But as we sort of look to the future and we look to very fast charging and And what that means and what the implications of that are is that we actually have to develop a system that operates independently, each one of these 400-volt modules, that balances those cells, and it does it very, very quickly. We're also doing cell balancing in between the modules. So as these modules are charged or used throughout the life of the vehicle, where each one of these BMS systems communicates with the other one and says, hey, this is where I'm at, this is where you're at, I'd like to give you something. And it does that in such a way that allows that to transfer between them. And of course, it is all managed by what we call an energy management system. It's this sort of overarching system that doesn't just handle the batteries, but it also handles the thermal management systems, whether it's heating and cooling. It's managing the power distribution systems, whether it's 12 volts, 24 volts, or 120 or 240 volt AC systems, as well as the 1600, 800, or 400 volt output. And then, of course, charging. So in our particular architecture of the battery system that we're building, it's completely self-contained. We don't necessarily have to communicate with the vehicle control unit. We don't have to communicate with any other peripheral systems to engage with, say, a charging station, whether it's the Atlis charging station or a CCS module. All of that is self-contained in here. The logic and everything to actually do this fast charging system, all of that, of course, is contained within that battery management system, as well as all of the thermal management stuff, which I'll talk about here in a second. But as we sort of look to the future, we picture this as not just something that shares between other systems in the vehicle, although there are some efficiency things you can do with that. We found that it was much more important to keep that self-contained and keep that battery system managing itself. It understands its current condition, it understands what it's doing, it understands what needs to be done, it understands how to maintain itself in its current state. It can also, if one of these dies, or maybe a number of systems die in there, one of these can actually pick up the load that the other one actually had. So we're building in redundancy in there as well, because it's super important that if one battery management system goes down, the whole vehicle doesn't necessarily die on the side of the road, especially if, say, you're towing or doing something like that. Now, on top of all of this, the one thing that we don't talk about is redundancy, because at Atlis, we are doing steer-by-wire and drive-by-wire for the vehicle. That's important for that modular aspect of the XP platform. To accomplish that, yes, this system does have a 12-volt and 24-volt output, but we actually have a lithium titanate-based 12-volt backup system. And that particular system is designed in such a way that if the main pack does fail, and that one catastrophically goes dead, if you're driving down the road, your steering, braking systems, light systems, everything works long enough for you to safely pull off the side of the road. You may not have any power available to you, but you can still steer, you can still brake, you can still operate all of those primary safety systems required to move you off to the side. To do this, though, we have to build a secondary pack or secondary module. We chose lithium titanate to be able to accomplish that because we wanted redundancy. We didn't want the headaches that lead acid batteries bring with it, but we also wanted a system that could do high power output as well as very, very fast charging. For example, if that does occur, or for some reason we use that 12-volt system to power that vehicle while the main pack is off, when that main pack is charged and then the vehicle starts to power back up, it's going to output 12 or 24 volts, but we want to make sure that we can charge that backup battery system as fast as we possibly can, because the idea is that once you start moving, that's your safety net. That's the thing that actually has to work. And by designing it from a lithium titanate-based chemistry, we get high cycle counts out of that. We get high reliability out of it. We don't necessarily have to worry about low temperatures and high temperatures and what's involved with that, but we can dump a lot of energy back into it. We can pull a lot of energy back out of it. Yes, it's a little bit larger system, but we can do that safely. It gives us confidence, and it's that backup system that's super important. Now, as we sort of look to the system and what else is unique by it, remember I talked about some of the cooling mechanisms, whether you're running a tube next to the cylindrical cells like Tesla does, whether you're running a cold plate underneath it like a large majority of the market actually uses today. There are a couple of EV makers out there that actually do something very similar to what we're doing, where we actually submerge the cells in coolant. We use a silicon-based mineral oil solution, very similar to what's used in power applications today. And the reason why we do that, in fact, we have no glycol systems anywhere in the vehicle, is because when we start looking at glycol-based systems, the problem with those is that anytime you get contamination within that high voltage system, you run the risk of a short, you run the risk of a fire. Anytime you actually get high voltage and water and aluminum in the same system, you get a chemical reaction there where it starts to eat away at that aluminum. We've actually seen that when we're doing some pouch cell testing where we get contamination in there. It eats through that outside layer, contacts that lithium, ignites, and then away we go. So nowhere in the vehicle are we actually using a glycol-based cooling system. For the battery pack and the motor controllers particularly, but for the battery pack system, we use a self-contained silicon-based mineral oil solution. And it's all designed to basically flow through a valve system. It'll either heat it or cool it depending on the application. And then, of course, it runs through and flows through the battery pack. Now, I mentioned before, remember, we're pulling energy out of the top and bottom. That's critical. We don't run fluid along the sides of those cells because, one, the cells could either be super long or super thick. We want to make sure that we can pull energy out of the top and bottom. And we could do so very efficiently with what we've done from a mechanical design here. The second thing is, this is completely self-contained, again, because we don't want to share that with the in-cabin systems. We're building a very modular product here. We're looking at something where the drive modules can be swapped out and swapped back in for something else, whether it's the front one or the rear one. We're looking at a battery pack that can be swapped out and swapped back in if it needs to be changed in the field. We're looking at a vehicle cab that could be a truck, it could be a van, it could be a box truck, it could be various different things. We don't want to complicate that system by sharing cooling systems and adding complexity to it. We also do this because we've reduced the number of connections that are actually involved in this. We went with a submersed pack because we simply have only a few connections that come out for some of the heaters and heat exchangers or the cooling systems. But we minimize the number of connections that are inside there. We don't have a lot of complexity inside that pack, and that's super important. We do have some complexity from a design standpoint because we need to make sure fluid is flowing appropriately and we're properly cooling in various different locations, but we eliminate a large number of components that are involved there. We are trying to suck that volume down to the minimum amount possible because this fluid does add weight to the vehicle, and that's super important. But current estimates right now put our largest pack, which is 250 kilowatt hours of usable capacity. Currently, we're looking at about 4,500 pounds for that pack. That's not the lightest pack that's out there, but it's also by far from the heaviest pack that's out on the market today. And this, to us, is very, very much so unprecedented in what we're doing. So by delivering a pack that weighs this much at the largest configuration, on top of that, some of the other vehicle components that are involved, especially when we start talking about a one-ton vehicle, we're trying to keep the weight of the vehicle down to around 8,500 pounds to 9,000 pounds for a one-ton vehicle. And that is aiming to be compatible with, say, a one-ton vehicle that you can buy today. How we're doing that, one is removing complexity in that. Number two is, with this custom cell design, we can actually pack things in very, very tightly. We can stack these things next to each other. Because we're not worried about heat transfer right now in between cells. We're pulling heat out of the top and bottom. Remember, we talked about that before. So we can pack those cells in very, very tightly. We can do small cooling channels inside there. We can pull energy in and out of it. We eliminate the number of components and everything that's involved there. And from a design standpoint, all of the battery management systems, all of that stuff is very compact. It sits kind of right on top of those cells. That's what we're developing today from that standpoint. So there's not a lot of extra volume there. There's not a lot of connections and traces and wires running everywhere. We try to eliminate all of that to reduce the number of potential failure points. When we talk about manufacturing, we talk about reliability and things like that. Reducing the number of components, reducing the number of connections, each one of those is a failure point. Each one of those is something that could fail down the road. It can fail in manufacturing. It's a potential cost adder. We're trying to reduce that as much as possible as we continue on. So cutting that down in half to a quarter of what you typically see in a battery pack today, that's our goal. And right now we're on track to be able to accomplish that. Now, the next thing that we're actually able to do with this is it becomes configurable to a point where we can scale it very easily. Today, in our vehicle configurations, we're talking about 125 kilowatt hour to 200 kilowatt hours to 250 kilowatt hours. 250 being the highest range 200 or 500 mile range pack. But what we can actually do is we can even continue to scale that. So when we start talking about the XP platform and what's involved there, we're talking about something that, yes, it operates a truck today, but we can move to a class 4, class 5, or class 6 vehicle that requires more capacity, more capability, more power, more range. All of those things can very easily be facilitated by simply just expanding on that pack, by expanding the number of perhaps parallel or series cells that's located inside there, or by using this system here, we can actually just stack a number of 400 volt modules in place to be able to accommodate the capacity or the range that we're looking for today. Now, all of this is super cool and it's super exciting, but the one thing we haven't necessarily talked about is how you actually charge something like this. If it's 250 kilowatt hours today, there is nothing on the market that can actually charge that in 15 minutes or less. And when we say 15 minutes, that's not necessarily 15 minutes from start to finish. The biggest challenge is we don't do preconditioning of the battery. We don't believe that while it is nice that you might click that in as a destination and you might travel there, it could be 5 minutes away, it could be 2 minutes away, it could be an hour away. We also look at the work environment and where people work. If you're using your truck for work every day, your job is very sporadic. You're not following the same pattern every day. You might be going to a job site here and a job site there. If you work in some of the services industry, right, you're doing something different every single day. There's no predictability there. There's no way to necessarily plan around that. You could be on the other side of town. You could be on this side of town. You could try time-based, but you never know if you have to plug in the middle of the day or the end of the day. So we look at the world as chaotic, and we're developing a system that can operate outside of or within that chaos, something that sort of solves the problem that makes it agnostic to the end customer. So what that means is when we're charging, between the point where you start and the point where you're full, and I hope everybody can see that there, we have to do a couple of things. One, we have to do the thermal conditioning of that pack, right? We have to do certain things there to be able to do that. We have to ramp up that charge and then taper it down towards the end until it's completely full. And then actually at the end, we do some more thermal stuff. At the end, we have to maybe cool those cells down, heat them back up, depending on the condition that we're in. So when we're looking at that total sort of workflow that's involved there, that's why we're aiming for something along here. We're in between here. We do 9 minutes and 26-second charge time. That is super important because there's other things that have to happen there. So what we're actually doing is from, when we say 15 minutes, we say from the point you plug it in to the point you unplug it, or you can unplug it, depending on what you're doing. But that period of time, that total time period from here to here is 15 minutes. That means we're doing conditioning of the batteries, we're ramping up the charge rate, we're charging those at the maximum rate for a period of time. Remember, we showed you that graph before. We're tapering that down, and then towards the end, as it sort of tapers down to zero, we're reconditioning those batteries for standard operation. Now, to be able to do that today with an existing pack design, or what a lot of people are doing today from a mechanical construction, is actually very difficult, especially when we start talking about ramping up the temperature very, very quickly, and start talking about pulling the temperature down very, very quickly. One of the biggest heat sinks you have is, one, the pack itself, but two, is that big body, that vehicle body that pack is stuffed into. So if you're trying to raise that temperature up and you're trying to maintain it, you're always going to be fighting that battery. And if it's super cold outside, remember we talked about dendrite growth? You can't charge a battery very, very quickly when it's cold. In fact, the probability of having a dendrite growth or dendrites grow inside that pack, especially at temperatures below, say, 40 degrees C, is super high, and it just increases as that temperature goes down. So when we talk about trucks and we talk about where they operate, we're talking about vehicles that operate in very extreme conditions, whether you're up north above the Rust Belt, or you're down here in Arizona where it gets super hot, where pavement temperatures can touch 160 degrees Fahrenheit. When we look at those two extremes, we have to deliver a consistent experience. It doesn't matter if you're there, it doesn't matter if you're here. Here in Arizona, I can go from hot temperatures, I can drive up north to Flagstaff, and I can go to super cold temperatures, and I can do that all in one day. So developing a system that can be able to handle that, a system that can take that into account and make that completely agnostic to the user, where it doesn't matter where you are, you get the exact same behavior. One way that we're doing that actually is we are completely insulating the pack. The pack is enclosed in, think of it like a big Yeti cooler. Think of it as this system where we have insulation between the pack itself and everything that's going on inside there, all the fluids and everything else, and the outside world. And that pack actually floats inside this sort of container. The container is very structural, right? It adds to the structural rigidity of the vehicle, but we actually do something from an insulation standpoint inside there. And we do that so that in extreme cold temperatures or hot temperatures, let's take cold temperatures. I grew up in northern Michigan where it can get below freezing, especially at night, and when the wind chill's super low, right, it gets incredibly cold. So when we look at conditions like that, one thing is, let's say you pull into your home, you park your vehicle at the end of the day, and the next morning you have to get up early and maybe you have to go out and do something. Maybe you work the roads, maybe you tow vehicles, maybe you work in some sort of service industry, or maybe you're operating an EMS vehicle like an ambulance or a fire truck. It's super important that the next time you get in there, that vehicle is able to perform. There's no compromise there. If the expectation is you're able to do something, you can do it. So we actually insulate that pack all the way around, and we're playing with different materials and things like that to be able to do that. We actually did some testing with some basic foam-based materials, again, very similar to what you would find in like a cooler system today. But what we're trying to accomplish, or what we are actually accomplishing in the test data today, is that if we were to talk about like day 0 or day 1 to day 7, we can maintain that temperature very, very close until about day 7, where it starts to really drop off. That means in order for us to maintain a high temperature within that pack, let's say you're in a very cold climate or a very hot climate, you're trying to keep that temperature from rising, that's very little energy we have to put into that system to be able to maintain that. And again, that is super important when we're talking about charging, but it's also super important when we're talking about operation of the vehicle. It's important that we maintain that temperature with very, very little inefficiency, that we put very little energy into that, so that the next day or the next time you get in there, you're not facing that challenge. We've all seen the stories of like starting a Tesla in the cold. I know even here in Arizona, when it gets a little bit chilly, when we start up a Model 3 and we start driving away, we always get that little sign that says regenerative braking isn't quite working right, or it's going to take time for the batteries to warm up to do that. In particular with a truck, we find that consistent performance is important. In our case, whether you're towing, hauling, or just driving the truck itself, we want to make sure that you get the same experience every single time. So one of the things we do is we're actually insulating that pack. That's also why we isolate those different systems from everything else. We don't want something else to bleed energy off the pack if we're trying to maintain that temperature at a level, whether it's low from ambient or high from super cold. We want to make sure that we're maintaining that temperature at its optimum point, so that every time you get in the vehicle, it's very consistent and you get that same positive experience. At the same time, when it comes to charging in cold or hot temperatures, we don't want to spend a lot of time trying to heat that thing up. We don't want to have to take 40 minutes to be able to do that. We don't want to ask you to drive 80 miles at some particular speed just to note that you can actually do that. The most important thing that we do is, regardless of what you have done, regardless of where you are coming from, that you get a very consistent experience when you charge. So again, we're isolating that thermal system. We're wrapping that pack in an insulation enclosure. That's one of the sort of IP things that Atlis is doing that's very different to the rest of the industry. That's something that is super important to us. Now, when we talk about all of this thermal management and things like that, one of the things a lot of people don't talk about, and I touched about it a little bit, is regenerative braking. There are two challenges with that we see. One is the most important one, is when that pack is full, you can't do anything from regenerative braking doesn't work. From our perspective, that's an inconsistency in performance. Now, we could do some things because we're doing drive-by-wire steering and braking. We could do some things electronically with the friction brakes to give you the same experience regardless of the pack is full or not. But from our standpoint, we find it super important that when you press on, say, the brake, or if you're doing one pedal driving, you let off the gas, that you get a very consistent experience. It's odd to me to think that, well, when my battery's charged, I have to change my behavior, and I can't predict that. But if it's somewhere in that sort of below 90% range, I start to see consistency until it gets a little bit towards the center right, and you see better consistency. That's not an experience that we find positive. So not only are we doing things from a pack perspective to ensure that there's a buffer there, which a lot of everyone basically does, but we're doing some things to ensure there's a buffer up there such that when you start to drive, regenerative braking still works. We're also doing some other things from an IP perspective to ensure that regenerative braking, or that experience of regenerative braking, is consistent even when the pack is full and perhaps you can't dump energy back into it. That's one of the things that we're trying to focus on. The other side of that is when it's cold or it's super hot. I actually experienced this weekend coming down from the mountains in a Model 3, was that if you're consistently using that, right? If you're driving aggressively and in a truck, remember you're towing, right? You're hauling things, you're towing heavy things, and that's all super critical from an operation perspective. That means you could be hauling 3, 4, 5, well, probably 4 times the mass of that truck behind you. And having a consistent experience is incredibly important, but also not running into a scenario where perhaps throughout you're going up and down the mountains, you're going up and down hills, whatever that happens to be, you come up, you start to come back down, and all of a sudden that regenerative braking capability is not there anymore. By doing things from focusing on a charging perspective, an energy dump perspective, as well as a couple of things from an output perspective, our ultimate focus is such that when you're operating a truck, as a truck is truly meant to be operated, that you don't have a compromise in that experience. By doing things from a charging perspective and what we're doing there, being able to dump a lot of energy into it and consistently do that over time, being able to pull energy out of it and be able to consistently do that over time, because we're really managing some of the thermal characteristics and things we're doing mechanically, as well as the selection from a chemistry perspective, is that we're actually able to achieve a scenario where you get consistency. You don't run into these scenarios where it tells you you can't operate the vehicle like that anymore. And if you're ever towing a heavy load downhill, the one scary thing is when your brake behavior changes, whether it's brake fade in the friction brakes or in the particular case of regenerative braking, if there's a change in that behavior. That's a difference in characteristic that you have to account for. And if it's cold outside and it's icy and you've sort of learned how to manage driving in that particular scenario, granted there's electronics and everything else that's occurring, but if you kind of learn how to drive that way, you know how to safely do that, you know how to handle those various different conditions. When something changes, and it's sometimes drastic, and you have to change your behavior, that can lead to an accident. That can lead to a problem that potentially somebody gets hurt. And we find it very important that we solve problems like that. So again, just to sort of summarize what we're talking about here, Atlis Motor Vehicles, again, we are an electric vehicle technology company. Yes, we're building trucks and we're building the technology that allows us to go there. But what we're really focused on right now, at least over the next 9 to 12 months, is getting some of this technology out into the market. It's finishing the XP platform. Yes, we are working on the XT pickup truck, but it's really sort of focusing on getting this battery technology to a point where it's in production, where it's usable, where we can actually start marketing this. We can put it in vehicles. We can start testing. That's one of the more important things that we're doing. We do have kind of a roadmap sort of built out as to what that looks like. Yes, we are still raising money as we kind of look to that and we look to the future, but our focus over the next 9 to 12 months is very much so on bringing all of this technology to fruition, to production. It's building up facilities in-house to be able to accomplish that. Now, a lot of people have asked how or who is going to build our battery cells. We have three vendors that we're currently talking to start early stages of production of an Atlis custom battery cell that we are currently developing that does a number of these things here. Our long-term goal, of course, is to work with a partner or bring in additional resources in-house. We believe that owning cell production is really key to the future of any company that's in this particular space. If you're reliant on suppliers, they own your destiny, and you're also fighting with everyone else that's out there in the space. And being a young, early startup, one of the challenges is if someone else drops $1 billion check on the table, who are we? So we look at where the future is going, where the opportunity is. Today, we have 3 different companies that we're talking to about this custom cell design that we're actually developing here. The pack itself and that overall construction, that will be done in-house right here in Arizona. We have no plans to outsource that to anybody else. So that'll actually start in our facility up north in Mesa towards the end of this year. We'll start low volume production of the pack and the different components of that there. But of course, for the cell production, early stages right now, our plan is we're engaging with these 3 different potential suppliers to work with us in getting low volume production going by the end of this year. And then subsequent years in 2021 and beyond, we'll be looking at whether or not or how actually we can bring that in-house and we can start to own that production. The intent is to do all of this here in the United States, at least as much as we possibly can. That does mean that we'll have partners that obviously work overseas, whether it's material extraction or a combination of those things, getting some of the different components together. But the ultimate goal is, of course, to bring this here in the US. It's to bring this close to us, to own our own destiny. And if you want to do that, if that's not in your business strategy today from an electric vehicle company perspective, you're going to face a lot of challenges down the road. There's a lot of different hiccups there. And you're seeing that with some of the OEMs today. They're starting to understand that. They're starting to get that. That's been in our plan since day one. We want to own our destiny as we sort of march forward, and we look to the future as this one of the biggest opportunities that we have. Now, in particular with battery technology, we also see opportunities beyond the electric vehicle space. Of course, there's energy storage, there's in equipment spaces, whether it's heavy equipment, whether it's agriculture, whether it's homes energy storage and things like that. So we're definitely looking at those opportunities. It really just depends on where we need to keep our focus right now today, which is in the XP platform and the XT pickup truck and the battery cell technology there. But of course, this is always applicable with either partners or various different verticals that are out there and that exist today. From a roadmap perspective, like I said, over the next 9 to 12 months, our focus is entirely on getting the battery cell technology to production, getting the XP platform to production, and of course, getting that production prototype of the XT pickup truck, getting that out to various different customers, getting that into low volume production, and sort of where we go from there. In terms of kind of where Atlis is at today, we are still a small team, but we're hoping to grow to about 75 individuals by the end of this year. We'll be 130 by Q1 of next year. We're a very lean company. We are not a traditional OEM development company. We definitely follow more lean startup practices. We definitely take on more roles. Everybody is juggling a lot of different things, but the team is growing. The facilities are growing. We've got a lot of opportunities and a lot of possibilities as we kind of go on for the next couple of years. Now, of course, right now, today, as you can tell, I'm working from my house. In fact, our entire team is working from their homes. And one of the emphasis or one of the key sort of things here is that we fortunately work with a fantastic team that's doing some really great things. They're able to develop hardware from their own homes, whether it's in their garages or maybe we trade shifts. One or the other goes to the office to take care of that. But one of the other things that we're doing, and I think this is actually a fantastic opportunity for us, is while we have this downtime, while everybody's at home, we have about 12 3D printers. And one of the things that we've decided to do, there's actually a company in California that's doing this. We're actually utilizing our 3D printers to start printing face masks and face shield components for various different companies out there. We're doing what we can to help. We are still marching forward. We are still pushing things forward. We are definitely not stopping. That's something we don't do. But we have this opportunity to help. And, fortunately for me, I work with a fantastic team that sees an opportunity like that to help, that sees an opportunity for us to make a difference. Yeah, we love to make a difference here, but if we can do that in any other way, we're definitely going to do that. So we're using all of our resources here to start 3D printing face shield components, mask components, whatever it is that we have. And if anybody else is interested in doing that, we are sharing the files for that. We're also sharing some information as to where you can send that. You can check that out on our Facebook page. We'll post some stuff in an email. And we'll, of course, continue to post on social media with that information. But if anybody's curious, send us an email to info@atlismotorvehicles.com, and we can share that information with anybody who can help. Should absolutely jump on board and help with this. So I believe that's everything I have to cover for today, and we are going to open this up for questions. I'd love to answer any questions that anybody has, whether it's about the battery technology, where we're going, anything about myself that you're actually curious about, or anyone on the team that I can answer. I would totally be willing to do that. Thank you very much for listening to me.
Mark, the largest question by far is, where's the battery demo?
Where's the battery demo? All right, so about a month ago, we did a battery demo live. We covered it up with a box. And the reason we did that is because we weren't yet ready to sort of share all the nitty-gritty details with that. There's an image that Annie could potentially pop up here. We have another battery pack system that is in development today. Unfortunately, due to this COVID-19 issue, everybody's sort of working remote. We were going to have this demo ready today. We think it'll be ready no later than next Friday. But basically what this is this is going to be a pack that is self-contained. Remember I talked about how a lot of the stuff is self-contained here. Some of the things we're doing from a thermodynamic perspective and things like that, that's all contained within this pack. We are actually going to go out. We're going to do a live demo of that, a live broadcast of charging that thing in less than 15 minutes. And that's from start to finish. That demonstration will be ready no later than next Friday. And hopefully we'll do another sort of big demo. Maybe well, everyone's in kind of a house arrest right now, so we'll probably only have 1 or 2 of us there while we do it. But we're going to go out, we're going to demonstrate that charging and that pack system. Unfortunately, with the whole sort of stay-at-home order, especially here in Arizona, and the team having worked remote, yes, we're still marching forward. You've seen some pictures of people working in their garages and everything else, but our suppliers have slowed down. A lot of the effort that we've been able to typically accomplish where everyone's together and they're really hunkered down doing that, unfortunately, it's slowed down a little bit. We just barely couldn't make it for today, so we're committing to a week from Friday to be able to go out and show that. We'll have 1 or 2 of us out there when we do that. We'll do a live demo for everyone.
Great. And another question is, how is range affected by towing?
So how is range affected by towing? That's a really great question. So typically, obviously, you start with a base range, whether it's 500 miles, 300 miles, 400 miles. Those are the 3 levels that we're currently talking about offering. The biggest factor in range is aerodynamics. So depending on the trailer that you're towing, it could be a little tiny trailer that's very aerodynamic. If you're talking about towing RVs, right, it's a difference between, say, an Airstream, which is somewhat aerodynamic, to maybe a big boxy RV trailer. When you start factoring that into it, that has a tremendous impact on towing range, just the aerodynamic aspects of it. Now, here at Atlis, when we design the pickup truck and we design everything else, we try to be as aerodynamic as we can, but we're trying to take into account the fact that we know when you start towing, everything goes away, right? Everything sort of goes to crap from there. So by designing the application and the use case, by focusing on that, we are going to see an impact on range when you start to tow. The other side of it, of course, is obviously weight. When you go from, say, a vehicle that we'll pick 9,000 pounds, we go from something that weighs 9,000 pounds to an additional few thousand pounds, maybe you're up to 15,000, maybe you're all the way up to 35,000 pounds, you are going to see a drop in range. And that's why I wrote this number 150 miles here. I know in my truck, in my particular pickup truck, if I tow at the max range, I see somewhere a little bit above 200 miles of range, and I start at 430 miles. Or I'm sorry, 530 miles. From our current estimates at a full load, 35,000 pounds, we should see that range drop to about 150 miles, which again, you will see a similar behavior in a full-size pickup truck. There are things you can do in trucks today, like additional gas tanks and things like that. But no matter what you do, you will see a drop in range while we're towing. So again, going back to charge times, if it takes you an hour to charge to get a full 150 miles, that's a lot of added time to your drive. But by pushing things down to 15 minutes, we start seeing something that's much more practical, something that's much closer to what you see today.
Awesome. And we have a lot of questions about charging. First one, can other vehicles use the Atlis charging network? And follow on, this one's related. Is the truck compatible with CCS or CHAdeMO, or will there be adapters available?
So to answer the first question, can other vehicles use the Atlis charging network? The answer to that will be yes. And our strategy here is to complete development of the Atlis AAC, and then we'll basically open up that protocol, the drawings and everything else, so we can actually get other people onto that network. As long as the battery within that system can handle that, or it can handle the power output, that's totally fine. The Atlis charging station is 1.5 megawatts at its highest sort of peak output. Peak output from a voltage standpoint is going to be 1.6 kilovolts at 1,000 amps. And just as a demo here, this is the current prototype we have of it. This is the charging handle for that particular system. On the end here, you have positive and negative. It is wireless communication with the charging in terms of how it communicates between the two systems. There is an NFC and a security aspect of it as well. But this is the current handle that we're developing for that particular charging station. The concept is that it is very similar to what you have from a CCS perspective. It's very similar to what you have from a Chatamos perspective in terms of handleability. I didn't touch on that too much, but the biggest challenge there is, again, it's in the handle. You can't read my handwriting. Probably can't read it from there anyways, but the other side of it is actually in the cable. There is no cable design today for a 1.5 megawatt system that we've seen anyways, that is very flexible and usable by anybody on the market. I have a standard that we've set. The standard is my 80-plus-year-old grandmother should be able to operate this system. She should be able to use it as though she's pumping gas into her car. So it's very important that we get that handle down to something that's small and compact. And as you can see there, we're close to a CCS handle today. We're actually very, very close. But it also is super important that you can handle that the cable remains flexible. And there's some proprietary things we're doing from a cable design, some lessons that I've actually taken from a previous project that I worked on in my past that will allow us to create that flexible cable. We have some prototypes in the development phase right now. Hopefully we'll be able to show that off in another 6 to 9 months when we sort of debut the charging station. Now, will this be compatible with CCS? Yes, but when we talk about CCS, when we talk about power delivery, remember today the AAC to do 50 minutes is 1.5 megawatts. The problem with some of the charging technology today is CCS. I believe the highest one that's out there right now anyways is 350 kilowatts, and it's up to 1,000 volts and a few hundred amps. Now, the challenge with that is that if we have a 250 kilowatt battery pack, you obviously can't, with 350 kilowatts, charge that in 15 minutes. There's just simply not enough power to be able to do that. We will be able to facilitate a charge time that's something less than an hour, of course, but unfortunately with CCS, you simply won't get the speed out of it. And this goes back to the question everybody asked me, which is, you charge a small battery pack, how does it scale to a large battery pack? And the reality is, it scales very easily to a large battery pack, but if you don't have enough power, if you don't have a big enough hose to fill that bucket, then it doesn't really matter what you're doing. The cells in the pack can only accept so much energy, so you can either have a really big hose, but you can't pump a lot of that in there, so you got to slow that flow rate down, or you have a really small hose and a really big bucket. Those are the two challenges that you have here. Ours is being developed to work perfectly from a high-speed rate at 1.5 megawatts. We're also looking to the future as to how we can actually increase that charge rate and those charge speeds. We do believe in the future we'll start seeing 5-minute charge rates, but if you're using a CCS or J1772 for at home, you'll be able to use all the way up to the maximum output that you can get from any CCS charging station that's on the market today.
Okay, and can I fast charge at home, and how is the grid affected by this amount of energy?
Okay, well, fast charging at home, if you have the money to be able to put a 1.5 megawatt station there, then obviously you could fast charge at home. Although your home supply from the utility company, you won't have enough energy to be able to do that. But can you charge at home? Absolutely. Again, there's a CCS 2.0 connector that we're putting on the front of the vehicle, and that will allow a J1772 home charging system, or if you have a DC charging system plugged into your home that can supply a certain amount of power there, then you can absolutely charge at home. But you won't necessarily be able to fast charge unless you can get enough energy from the grid. Now, to answer the grid question, in certain areas of the country, there is no negative impact to a 1.5 megawatt charging station. In fact, we met with a number of utility companies and talked through the different scenarios and the different deployment conditions. And even if today they can handle the small deployments, they are all looking at scaling up to be able to handle what the future is there. But when we look at sort of how do we deploy charging stations quickly, how do we solve that problem? If we're trying to integrate a 1.5 megawatt charging station into the grid, we're talking about a cost that could go up to $1 million per station as we look to plug that in, depending on where you are. In some cases, it could be significantly less. In some cases, there's a shared cost model there. But in order for us to be able to do this quickly, we're actually looking at a scenario where we would basically have, I'm just going to write a battery buffer in between there for the charging station. And what that allows us to do is then this is then connected to the grid. What that allows us to do early on in the process is deploy something very, very quickly, very, very cheaply. We can plug into the existing infrastructure that's there today, There won't necessarily be a ton of vehicles out there that are using this, but if there are, we can start scaling this battery pack and some of those connections to be able to do that. We've got a couple of different sort of business models and product designs that we're looking at where we can do a single deployment for a single station. And that's super important, right? We get that frequency up. And if it's 15 minutes, there's not a lot of wait time there. But we can actually do something that's larger, that's say a 40-foot container that would actually be able to support up to 8 vehicles simultaneously at one time. And again, when we talk about consistency in everything that we're doing, what we mean by that is that when you plug in, there's no shared connection between you and another person. If there's a plug available, you get 1.5 megawatts of power. You don't have to share that between the vehicle next to you.
Okay, and this is sort of related as well. Can we trickle charge with 120 volt maybe from solar panels? Speaking of, will stations run on solar?
So will stations run on solar? Yeah, there is a model built out to be able to actually charge that battery pack system from solar. It would take a fairly significant number of those to be able to drive throughput for, say, 1.5 megawatts. That's a little bit unrealistic today, but I think that's realistic in the future. In terms of charging your vehicle at home or through solar, 120 volt system, the answer to that question is yes. But if you're talking about a 120 volt system that's maybe pushing 20 amps in that particular case, right? And you're talking about a 250 kilowatt system. It's a very, very long time to be able to do that, but you can absolutely trickle charge that system.
Excellent. And someone wants to know, where can I get that sweet shirt?
You can get this off the website, actually. It's if you go to, I believe it's shop.atlismotorvehicles.com, you can buy one of these shirts from there.
Awesome. Are graphene, oh, I hope I don't pronounce these incorrectly. Are graphene, glass, or vanadium materials being thought of for use in the batteries, and what are you doing about cobalt?
So to answer the first question, there's a number of different materials that we're looking at from a battery perspective. I'm not necessarily going to go into details with some of those things and maybe share what we're looking at from that standpoint. But on the second question, what are we doing about cobalt? Obviously, that's a very conflict-ridden material. We are definitely looking at different solutions as to how we can minimize that, to eliminate that eventually. The ultimate goal, obviously, is to eliminate some of the more conflict-oriented materials from either the vehicle assembly to the battery systems and things like that. That is definitely high on our list of priorities as we kind of progress through. But we do also have to keep in mind that it's a progressive thing for us. So we are a small company today. As we sort of look to grow, we'll be looking at how we can source material to avoid those complications.
Okay. Where does Atlis get its money?
So currently today, we are 100% funded either by the founders like myself in the beginning, or we've gotten a lot of our funding from our potential customers. And we love that aspect of this. We love the idea of building a company that, one, our customers can share in our success, they drive our success. That also means we don't necessarily answer to pressure from outside of them. All of our pressure, at least currently today, comes from the end customer and what they want to see us do and whether or not we're making the right decisions from there. That being said, currently we do have a $25 million round open that we're talking with a number of private investors about and looking to close that. And of course, we have follow-on rounds that are slated towards the end of the year.
How do I contact Atlis directly?
The best way to contact us right now is info@atlismotorvehicles.com. If you send an email there, then that'll get directed to the appropriate person that can answer your question.
Does fast charging reduce battery life?
Yeah, in certain ways it definitely does. If you remember, maybe you weren't here for the beginning of the presentation, but we take into account from a design perspective the change in battery life over time. And again, it's aiming for that consistency. So if we say in 10 years, you're going to get a certain experience that was very similar, if not identical to the experience from day one, we take that into account as we design the system. So yes, Fast charging it can reduce the life of the cell, but as I talked about earlier, some of the things we're doing from a design perspective, chemistry selection perspective, and thermodynamic perspective allows us to minimize the impacts of fast charging and reducing battery life. Current indications from the tests that we have say we are definitely going to hit our 2,000 cycle, 1 million mile requirement.
Excellent. And how will Atlis compete with Ford and Rivian?
Currently Rivian is primarily focused on adventure vehicles. They do have a work model with Amazon, but from what we can tell today, they're primarily focused on work vehicles. Ford is focused on consumer and transportation today with their electric F-150. The way Atlis is really targeting this and the way we're approaching this is we're work dedicated. We're not going after consumers. We're not necessarily going after adventure. If you do so choose to do that, we love it. We're also very aftermarket friendly. So if you buy an Atlis truck and you want to do something to it that allows you to take it off road, to do something better from an adventure perspective, or do something that's maybe much more you, we are an aftermarket friendly company, which means we want to open ourselves up to those that do things to their vehicles that fits their particular application. But from how do we compete with Rivian and Ford? One, we're targeting work markets. We're very central to that particular aspect of it. Two, we are not an electric vehicle company. We are an ecosystem-driven company. Yes, the vehicle is the entry into that particular market, but we are definitely looking at that technology and how we can actually focus on building that entire ecosystem. And of course, the biggest differentiator for us right now is the battery technology, what we're doing there that makes an electric vehicle from Atlis practical versus something that's much more of a compromise.
Excellent. We got a couple more. Will Atlis motor vehicles support bidirectional charging for home emergency power applications?
That's definitely a question that we haven't yet answered. I'm personally not a big fan of vehicle to grid, but if it's vehicle to the home and we're charging that home, I think that's a very usable aspect. The other side of it that I will say is that when we talk vehicle to vehicle, technically today there's enough power in the Atlis vehicle, and with a 240 volt, 40 amp circuit, you can technically charge your Tesla, your Leaf, your Rivian truck, whatever it is. You could charge that vehicle from that particular power output. It's basically a J1772 solution between the two.
Okay, this one's sort of related. If we have a power wall or home power pack, can we use that to charge the vehicle?
You can, but obviously it would have to be big enough to be able to support both your home as well as the vehicle and however much energy you want to transfer to that. One possible scenario, and obviously Atlis is looking at very similar solutions from a home energy perspective, is that if those two systems are communicating, then we can set up certain criteria to determine how much energy goes into the vehicle, how much stays in the home, to make sure that we're not making compromises either way.
Okay, and I think this will be our last question for tonight. We have a ton of them in the chat, but we'll be sure to answer them on social media and whatnot. Last question, can anyone join or contribute to a crowdfunding campaign, including foreign residents?
Excuse me. Yes. However, there are certain countries where it is not allowed. Canada, the UK are the two biggest ones. Unfortunately, that is not up to us. That is not even up to the US. That is a very Canada-specific thing or a UK-specific thing where they do not allow you to participate in crowdfunding campaigns for companies that are based here in the US and raising money here in the US.
All right, that was our last question.
All right. Well, hey, again, I appreciate everyone's help. If I cannot stress this enough, the COVID-19 thing, it's a very serious thing for everyone. If you want to participate, if you have 3D printers, if you want more information, please check out our social media pages. We'll send out an email here, hopefully in the next couple of days with more information. We're willing to share that, make some face shields, build some masks, help out however you can. We appreciate that help. We're a big community. Everybody's here to do the right thing, and we appreciate everyone jumping in and helping us out with that.